Then we ended up at green theorem. Okay. So what does green theorem say is that imagine you have some region which is Houdini type 1 and type 2 both. That's just one example of it. But you have a green region. Okay. It's a green region. And what do you mean by green region? So it's type 1 and type 2 both. Type 1 plus type 2 both. Okay. And then draw a bigger picture. So I have this region, and you can see, call it type 1 and type 2, the green region. This is just one picture. You can have other green regions too as well. And assume that C is the curve that we can treat it as the boundary of this green region, and this curve must be a rectifiable curve. It must be a rectifiable curve. Now, what does green theorem says that and in this region, imagine you have a vector field actually defined over it. Okay, so you have a vector field defined over this region. And what green theorem is saying roughly, that if you take these really microscopic circulation, the microscopic curves in the entire region of the field, okay? If you're going to take these microscopic circulations in the entire region, right, and add them, so if I call this region as S, and add them all, you're going to get this, kind of a global circulation of F around the boundary actually. Okay? Global circulation of F around the boundary. Now what is, so if F is, a vector field with the two components P and Q, where P and Q are scalar value. Okay? What is the meaning of curl in two dimension? So we know that the meaning of curl in two dimension is this actually, is partial Q by partial X minus partial Q by partial Y. Okay? So this is like microscopic circulation at for example, at an arbitrary point. And then you're saying that if you combine them all, okay? If you combine them all, in the given region X, Y, what you're gonna get? You're gonna get the global, circulation of this vector field F around the entire, what do you call, the curve. Okay? And I know that in a classical sense, I can also write it as P dx plus Q dy actually. That's what essentially the green theorem means, that if you take the local circulations in the entire region and put them together, sum them up, you're going to get a global circulation of F along this curve. That's what essentially. Okay, so we proved it in detail as well. Now, what is the serious limitation of this result? This result demands a lot in its current form. Demands a lot. This result is true only in those regions which are green regions actually. In other words, they are type 1 and type 2. The question is, what if I don't have a green region actually? Am I going to have a similar kind of, for example, region? In other words, imagine I have a region which is only type 1, for example. So can I have a green theorem here? Or I have, for example, a region which is only type 2. Or a region which is neither type 1 and type 2 actually. Can we have it? The answer is, in some situation, yes, you can. For example, take a region that is only, for example, type 1, that looks like something like this actually, okay? So maybe I must draw it carefully. looks like this. Something like that. So assume it's a symmetrical shape and looks both same way. Okay? Something like that. Now what kind of region is this? It's type 1, yes, for sure. It lies between two lines. Is it type 2?
No,
We can't say it's type 2 actually. So the question is, what should I do if I want to do some kind of apply the Green theorem in such kind of a region? Okay. Then you have this trick, what you call cut and paste actually. So what you're going to say, imagine I'm slicing this up into the two pieces. Okay, and consider each of the pieces. Now each of the pieces is a green region. Okay, so now you don't have it. So from the middle you are slicing it. Now it's green region. It's type 1 and type 2 actually. Okay, not together. And then what can I do? I can apply Green theorem here and apply Green theorem here. In other words, you calculate the circulation here and circulation here and add them up is going to give you the net circulation, local circulation, and similarly the global circulation as well. Okay, so that's what we're going to do. So so I'm just giving you, kind of a bit pictorial way of doing it. Okay, let me make it a bit precise. So this is a hypothetical line, okay? And then I want to consider, for example, and imagine, okay, so I need to obviously specify the orientation of, the curve for each of the part of the boundary, but like imagine that this part of the curve is oriented this way, okay? Okay, so in this manner, that's the orientation of it, all right? And for this curve, it has, for example, this orientation going this way. Okay. Now, imagine the boundary of the entire curve. I'm calling it C. Okay. And the boundary of each of these, imaginary regions, I'm calling it, for example, say gamma 1 and gamma 2 actually. Okay? Gamma 1 and gamma 2. Now let's talk about it. So I want to do what? And say this region is S1 and this region is S2 and the entire region is S1. So I want to compute the circulations, okay, and I'm also assuming that I have a vector field defined here actually. So let's collect all circulations of the vector field, okay, in this entire region. Okay, so let's compute the circulations in the entire region. Then, since this S can be split into two parts, so this would be same as the integrand is same plus S1 and S2. Right? Integrand is same actually. So you can split it into the two parts. Now, for S, I don't know that whether it's, green or not. But for S1 and S2, I know that they are green region, type 1 and type 2 both actually. So I can apply Green theorem here. Okay? So what would be the Green theorem here? Okay. So there's a bit difference. Calling this curve as C1 and this line as gamma 1 actually. Okay? And this curve is C2 and then this line is gamma 1 and this would be gamma 2, but gamma 2 is same as gamma 1 with a negative orientation actually. So if you wish you can call it, okay, let's call it gamma 2 for now. Okay. So this would be equal to the integral of say p dx plus q dy Okay? But what curve I am integrating? So I'm going to say C1 concatenated with the gamma 1. Okay? C1 concatenated with the gamma 1. Alright? Plus the other would be C2 concatenated with the gamma 2 and PDX plus QDY. Okay? I couldn't apply Green theorem here because it's not true in S, but it's true in this space as well. Now what can I do with this? I can say that this is same as I have a C1, okay, plus same integrand plus gamma 1, okay, plus C2 same integrand plus gamma 2, but gamma 2 is gamma 1 bar. Okay, so it's gamma 1 bar, so it's opposite, it has opposite, it's gamma 1 with the opposite rotation. So I can write a minus gamma 1 and I can get rid of this. So this would be same as that I have this PDX plus QDY, C1 concatenated with C2. But what is C1 concatenated with C2? That's really C actually. So I have C PDX plus QDY. So hooray. Okay. Now what's a good thing about this result? So that's a generalization of Green theorem. Okay. But now you no more need a Green assumption. So you made your assumption weaker actually. Now if you have only, what do you call, type 1 region, you can still apply the Green theorem to it actually. And if I, for example, rotate this picture and make it like that, then that would be type 2 actually, and the precise same reasoning would work. So it's also true for type 2 regions actually.
तो यहाँ पे जो gamma 1 और gamma 2 है, वो सिर्फ डायरेक्शन को शो कर रहे हैं या कोई रीजन है?
नहीं, gamma 1, gamma 2 ये कर्व है. इस कर्व का नाम मैंने gamma 1, gamma 2 का. ये जिसके थ्रू मैं स्प्लिट कर रहा हूँ इसको, imaginary कर्व. ठीक है? But इस कर्व को, this curve I'm making it a part of this actually. So when I'm making it a part of this, so it has this orientation. While when I'm making it, I can also treat this as a part of this curve, it has opposite orientation. Okay, so have a line, but you treat it as a bit different kind of thing. ठीक है? इसका ये तो देखो, यूपीएस को देखो, ये पकड़ने की आवाज़ें कर रहा है. बंद कर दो इसको, ठीक है? ठीक है जी. So what is the advantage to do now that we have extended the Green theorem? Now you can apply it to those regions as well which are type 1 and type 2 only. We can even take it to the next level. How about those regions which are not type 1 and type 2? Maybe, for example, this annulus actually, or this, what do you call it? Sheet. Shell actually, where this part is empty part. So it's like a disc. Okay? The trouble with this is that this is neither type 1 nor type 2, nor green actually. So कह सकता हूँ कि type 1 type 2 है. अगर ये ना होता है तो फिर तो ये type 1 type 2 है. But this inside annulus is creating the trouble. Okay? This internal curve actually. Not taking, so you can't, it doesn't fit into any category. Okay? So I would like to talk about such kind of reasons. Such kind of regions as well. Okay, so I would like to take this analysis to a new level. That the Green theorem is also true for what you call the Jordan regions actually. So that's a Jordan region actually. I'm going to define what you mean by Jordan. Okay, so here's a definition. So the definition says that let C be a curved segment. The curved segment, obviously in Rn, and with parameterization So I have a parameterization for this curve segment P, that is something from AB into I. Okay. I'm going to call this curve C, curve segment that is parameterization, that is parameterized by P. If I'm going to call it, say for example, closed, so it's a closed curve segment. If, what do you think, what should be the definition? So the yes, so it should, so जहाँ से ये start हो रहा है should end at the same place actually. PFA equal to PFP. If I have a curve that is, I'm going to call it closed if it is starting from the same point. Okay? I'm going to call this curve segment simple. Okay? I'm going to call it simple. If it doesn't intersect with itself actually. It doesn't intersect with itself. In other words, there are no 2 points in the domain where they agree with each other actually. What would be the meaning of it mathematically? You don't want your graph to intersect with each other. So what should I do? What should I say actually?
Bijection method?
I'm sorry?
Bijection method?
Bijection is too much. So if it is 1-1, it's enough actually. And if it is 1-1, in other words, for every, what do you call, input,
we have
we have output.
different output.
But, okay, we need bijectivity, yes, you are right. We
One
need
to one.
bijectivity. So if I yes, so it would be simple if you can have a point. You can have 2 points in the space which have the same input actually. Anyway, so it's simple if P is a bijection. ठीक है? ठीक है? I'm going to call easy definition. I'm going to call a curve Jordan. I'm going to say that C is Jordan if it is rectifiable. At the moment I don't have rectifiability here, so curve segment could have an infinite length as well, okay? Plus simple plus closed. Okay? So what do you mean by a Jordan curve? So Jordan curve is a curve which is simple, and okay, it doesn't intersect with itself, which is closed. Okay? So it starts from somewhere and ends at the same position, and it's rectifiable. It should have a finite length actually. So you're going to call it a Jordan curve.
सर
जी.
सर अगर वो कर्व सेगमेंट है तो मतलब उसकी लेंथ तो फाइनाइट ही होगी.
Segment doesn't have. We haven't given a technical meaning to segment actually. Okay, this is our intuition that we mean. So whenever segment comes in our head actually, we assume it has a finite length, but we haven't defined something being segment. To definition दी है कोई हमने? Have you given any definition of being segment?
But sir, if a line has some ending point, then it should be finite.
Okay. So
लेकिन सर जो सेगमेंट की बात कर रहे थे हम, तब जो पाथ की बात कर रहे थे तो वो A to B है जो, यानी कि उसकी डोमेन को हम रिस्ट्रिक्ट कर रहे हैं तो सर वो फाइनाइट होगा ना?
क्या मतलब?
सर ये
It's not
जो कर्व था हमारे पास सर.
देखना. So you want to compute for example, okay, सिर्फ domain restrict करना is not going to guarantee that it has a finite length actually. Because in order to compute the length, you need the derivative of P prime of T actually, and its magnitude, and we want to integrate it. So you can have a P that has a finite domain, but there can be points in the domain where the derivatives explodes actually, infinite हो जाता है. ठीक है? Asymptotic हो जाता है, infinite हो जाता है. Then you can't integrate it. So you can't say that you have a finite length actually. Okay? ठीक है? Is it making sense?
Yes, sir.
So is this a Jordan region? Is this a Jordan curve?
Yes, sir.
Yes, sir.
So type 1 curves are Jordan curves. How about type 1 and type 2? Would that be Jordan curves? So it's really generalization of it actually. So can you give me a curve that is not type 1 and type 2 but Jordan actually? Okay, let's first think about it. Can you give me a curve that is say closed but not bijection? Closed but not simple. Closed but not simple. Think about it. So it should be closed, should start from somewhere and end somewhere. But meanwhile, it must intersect with itself actually. That's what you want. So
we can give the shape in our mind, but we can set the shape, but we cannot give the formulation. Yes, sir.
So that's a closed curve segment, but not okay. It has one intersection. You can have multiple intersections. So it could be something like that. It's also it's closed but not simple. How about if you have can you think of a curve that is simple but not closed? That should be easy. What?
It can be straight line.
A line or maybe a curve, something like that. Parabola, okay, is simple, takes one-to-one values, but it's not really a closed curve. Can you think of something that is neither closed nor simple actually?
कोई सा लूप है जिसमें इंटरसेक्शन है लेकिन उसके एंडिंग और स्टार्टिंग पॉइंट सेम नहीं है.
Okay, so how should I make it? Think about something. 6 could be the one of the example. 6 could be one of the example. That it's not
9 भी है.
9 भी है. Could be anything. You can have lots of examples. Huh? So it's neither closed nor. Anyway, in the Jordan view, so simple, closed, rectifiable is Jordan actually. So you will see the Jordan is a bigger set actually. So that includes type 1, type 2, green curves, not
Like
green
green
curves,
curves.
but like type 1 and type 2 combination. Okay. But it can also, so it would be an interesting example, to find for example that is neither type 1 nor type 2 actually. Okay. So it would be, if you take for example these two concentric circles actually. Not talking about a region, but these two concentric circles if you want to treat them as. So it's none actually. Okay. It's none. Anyway. So the question is now what we would like to ask. Imagine I have a region that is enclosed by a Jordan curve actually. Question. Can I apply Green theorem there actually? Answer is yes, you can. Okay, so you can generalize it. Let's call those regions as Jordan regions. So Jordan region means a region which is enclosed by a Jordan curve. It's a Jordan region. So this is important. Think about it. If a theorem, so you have a physical situation that you want to model, okay? And you have a green theorem that only applies to green regions, or type 1 or type 2 actually. That means that if you have a complicated picture and you want to study, really combine all of the column within that region, so you don't have a mathematical tool that can help you. So if you have a theorem that allows you to deal to do, to sum up the circulation in that region, it would be a good thing. Okay. Imagine take this multiply connected region, okay? So imagine this region actually, okay, enclosed by two Jordan curves. Okay, enclosed by two Jordan curves. So I'm talking about this part, this region. Okay. ये वो है, वो क्या कहते हैं, ये होल वाली गोली है? हाँ? Donut कह रहे हैं. It's not really donut, it's shadow for donut actually. Polo, yeah, shadow polo.
Biscuit ही होने चाहिए.
This time भी हो सकता है.
ठीक है.
Time भी हो सकता है.
Party.
Well, it's a shadow of something like that. Okay,
So
it's
like
not really
black hole
visualized.
picture,
Huh?
like black hole picture, light is up there and
Yes.
in middle there is a black.
Tire का shadow. Something like that. Hey, ठीक है. So I would like to basically, can I apply green theorem in such situation? So our previous theorem doesn't allow it. Okay, but I know that it's sitting between, two Jordan curves actually. Okay. So it's sort of a Jordan region. Question is, what should I do? So cut and paste. So how should I cut and paste? So let's draw an imaginary line. It's an imaginary line, okay? It's not a part of the region. Okay? And consider this. So that's one piece. And the other is this actually. So it goes this way, goes this way, goes this way, goes this way, and goes this way, something like that. Okay. How can I do it? So let's give these curves names actually. So that's a C1, that's C2. So I'm not going to get into the every detail. So let's call this part of the curve, say C11. Okay, C11. So C1 का पहला part, C11. Let's call this C12. Let's give this name. ठीक है? इसको क्या नाम दें? Give it any name. Gamma 11 for example. Okay, going this way. And gamma 12. Let's call this gamma 1 and gamma 22 this way. ठीक है? So your task is to show, just play with it. What we did here, you try to do something with it. So this entire curve can be seen as what? So this half of it would be, for example, let's call it C21 and this piece call it C22 actually. So it's C22 concatenated with gamma 11 concatenated with C11 concatenated with gamma 21 actually. Okay? And you have other variable as well. Okay? So try to write a green theorem for it. So you will see that green theorem as well. You combine circulations here and combine circulations here. Yes, you can give this entire region name S1 and this entire region name S2 and the S is the